Good morning, everyone. First of all, my student didn't get a visa, so that's why I'm presenting here. Believe it or not, I have not presented a single technical paper in the last 20 years. So let's try. All right, so our work is to use language model, not large language model, to support tensor programming generation. So here, we are dealing with the challenge of tensor program generation. As everybody knows, obtaining high performance tensor programs, in this case, we mean low latency tensor programs with high efficiency, that means with very short compilation time, is critically important for deep learning applications. Meanwhile, the computing hardware architecture is becoming increasingly complex. As a result, to better utilize these hardware power, tensor programs need to make many decisions, which makes the problem even more challenging. Now, first, let's look at existing approaches. The first type of approach is pruning the decision space with heuristic constraints. However, here there are two problems. First, it's very hard to choose a suitable performance indicator, as sometimes a better indicator value does not necessarily lead to better performance. Sometimes, because of that, heuristic constraints prune away high-performance candidates, resulting in very poor performance. A second type of existing approach utilizes a search algorithm plus performance cost models to generate tensor programs. Here, measuring the latency of a tensor program is usually very time-consuming. So performance cost models are thus used to estimate the latency. Such models rely on very sound feature engineering, which can be very tricky. As a result, what's worse, this approach is not effective in utilizing the large volume of data. In this case, we mean tensor programs and their measured latencies for efficient tensor program generation for two reasons. One, traditional search algorithms were not really set up to utilize large amount of data. Second, these performance cost models usually have a small number of parameters with limited learning ability. So with the buzz of all the language models, we understand that language models can improve the learning capability and better utilize data by increasing the number of parameters, and this is a very nice feature to have. As a result, we propose to transform the tensor program exploration task into a language model generation task. So if you look at this chart, a language model aims to generate coherent and meaningful text for a given prompt. Our task is to generate high-performance tensor programs to given hardware and subgraphs, so they match really nicely. Now let's look at the overview. Usually, a tensor compiler has three parts: a graph processor, a tensor program exploration framework, and a code generator. And in this work, we focus on the middle part, and we call it tensor program generation framework, in which there are two components. The first one is space builder, so which builds an expansive tensor program exploration space, which can lead to high performance, meaning low latency tensor programs. The second component is generator, which develops powerful search capabilities within the search space. This leads to high efficiency. So if we expand these two components in more detail, we actually have 6 steps: search space building, designing tensor language, large-scale sampling, pre-training, tensor program generation, and iterative optimization. Next, I'm going to go through these 6 steps one by one. First step, let's look at how to build the search space. So here, our contribution is we formally describe the common generation process of optimized tensor programs. Specifically, given a subgraph S0, which can be a mathematical expression or a naive tensor program, we build the decision space. We design the sampling. We get the decision path. Then we apply this decision path to S0 to obtain Sn. So this Sn is what we call tensor program. So here, the performance of Sn is closely related to the sampled decisions. We next formally define this overall search space. What we just described is a single S0. So here, if we consider all subgraphs, we obtain a search space, which is the Cartesian product of all decision spaces. In particular, any decision path of the tensor program Sn in the search space S is valid. So here we answer a critical question. How do language models generate valid tensor programs? Here, we do not consider generating optimized tensor programs directly. Rather, we leverage language models to learn and generate the decision paths, and then we use the compiler, convert the decision paths to tensor programs. The second step is to design the tensor language. So here, we design our natural language-like tensor language. Our tensor language sentence consists of 3 components. First, an input subgraph. Second, the hardware specifications. Third, the decision paths. So below we show a couple examples of our sentence. Here, the token of each component of a sentence is flexible yet consistent. Third step is large-scale random sampling. So here we engage a large-scale random sampling of the search space to obtain an offline data set with our tensor language model can learn from. Specifically, it achieves the following objectives. First, it aligns the data distribution from the data set with the distribution in the search space. Second, it builds as large a vocabulary as possible. The fourth step is pre-training. So here, we adopt the architecture of GP2 small. We train from scratch. Approximately, we have 100 million parameters. TLM, our model, is composed of 12 layers, each featuring 12 attention heads and more than 700 hidden units. After pre-training, TLM can generate valid tensor language sentences. The fifth step is to generate the tensor programs from the sentences. So we first generate the sentences, like how the language model generates sentences. The language model probabilistically samples the next token to ensure the generated sentence is coherent and meaningful. Here, likewise, when generating the next token, in our case, we mean by the current decision, TLM combines the knowledge learned and the decisions made to probabilistically sample the current decision. So from the sentences, we can generate tensor programs. First, TLM extracts tokens from sentences, converts them to decisions. Remember, we do not generate directly, we generate decision paths, and applies them to the input subgraph to generate the tensor program. And this process is actually the exact reverse flow of the previously described sentence token generation step. So here, we already talked about the language models can generate valid tensor programs, but how about high performance? That's not sure. So here, this is the core idea of TLM. We use high performance tensor language sentences as demonstration data set to perform supervised fine-tuning to get high performance tensor programs. But here the question is, where does the demonstration data come from? So that leads to our sixth step, which is iterative optimization. Here in each iteration, we train our TLM model in a different fashion compared to the language model training. First, we substitute the reward model with actual tensor program measurement. Second, we employ iterative SFT instead of RL because RL is unstable sometimes. So here, the core idea is to use the best subset of the data generated, aka the demonstration data, to fine-tune TLM. There are two nice features here. One is TLM can generate better data iteration by iteration. Second, the latency of each iteration's demonstration data will converge after some point. Everything combined, our model TLM cannot generate high-performance tensor programs. So let me quickly go through the evaluation results. So this shows that the demonstration data, the latency does converge. And the convergence speed only requires 200K measurements on GPU and 300K on the CPU. Well, it may sound large, but this is an order of magnitude smaller compared to Tencent and the TLP, which usually uses like 8 million measurements. So it converts fast. Second, we look at the subgraph benchmark. We show that with a small number of measurements, like 10, TLM can achieve 103% and 95% of the performance of answer and the meta schedule after 10K measurements. And also, we show the end-to-end workload benchmark. So here we show that under a limited budget, TLM's performance matches answer the meta schedule, yet compiles 61 times faster. So that shows the high efficiency. And this is our last result. This shows that TLM has been implemented on actual systems and has led to significant performance gains. Well, to briefly summarize, we designed the language model-friendly tensor language to represent tensor programs. We also developed a tensor language model, TLM, to combine the knowledge from offline learning and previously made decisions. So enabling more effective search space exploration, leading to more efficient tensor compilation, which is very important for deep learning applications. Well, thank you for listening, and I'm ready to take questions.